Welcome to this review lecture, the final review lecture of this course. So this is a course on industrial math and computation. There is the modeling aspect, there is the mathematics, and then there is the computation. So I hope that with this review, I can illustrate the three aspects: the modeling, industrial math, then the math, and then the computation. But first let me explain what the final exam will be, or first of all, when the final exam will be. So this is not next week, actually not this month even, so still far away, but still think about it, because even though this course is focused on projects, participation to this final exam is mandatory to pass the course. So that is the um most important thing about the slide, um, except for the date, of course. So the exam takes place very early in the morning. You can go to the room, our room, where we typically met, or as this course is also a little bit of a hybrid, the questions will be emailed to you, no matter if you are physically on campus or not. So the exam can also be taken as an online exam. It's an open book, open notes, and you will need a computer. The most important part is again that it is mandatory to do. The second part is the date and the time. Then three, the exam must be solved individually. So you could work in pairs on the projects. You cannot work in pairs on this exam. Um, the answers must be submitted on time. That means at 10 o'clock on the same day. There might be a grace period with great scope, but don't push it. Don't email me at 5 o'clock or 10 a.m. the next day. Hey, can I still submit the exam? The midterm exam was rather heavy and difficult to do in time. I have limited the questions. Well, there are actually 8 questions, but if you do 5 of those 8, you will get a perfect score if you solve five of those 8 correctly. So, and you have 2 hours time. Okay, here is actually already one question on the exam, and that is to encourage you to participate to the oral project presentations, not only your own presentation, but also the presentations of your fellow students. So one of the questions on the final exam will be describe in one paragraph what you learned from another project presentation. So even if you are taking this course online, you could email your fellow students for the version of the slides so that you have an idea of what the project is about. Okay, so in this review, I will review 7 other typical questions. I cannot say that the 7 questions, together with the last question on this slide, will actually be exactly the shape of the final exam, but they're kind of prototypical. So you must also review the review for the midterm exam. Look at the homework problems. Some of the homework problems were mainly seeing if you understood certain aspects of the material. The midterm exam itself contains some good questions. So look at the answers to the midterm exam. I do not have the answers to the homework posted, but the answers for the midterm exam, they are posted. So in this review, we consider some of the most important problems, but the list is certainly not exhaustive, and I will try to indicate what is actually missing. Okay, see, I have 42 slides, so I hope it, there will be plenty of time to fill here. So we started the course in the first week with statistical reasoning, and one of the topics we considered was Taguchi quality control. So here is a question. We have to choose between two processes to manufacture watches. Um, and when is a watch okay? So you can leave a watch without adjusting for 1 month, and if the watches still give the correct time within 3 minutes after a month, then it's okay. Otherwise, if the deviation after a month is more than 3 minutes, then the watch needs to be discarded, and that comes at a cost of $10. Okay, in the past we have two choices. We have experience with two means of production. Watches of the first process, we call process A, they are actually always behind with 1 minute after a month, but the standard deviation is a minute. The second type of watches produced by process B, by the second process, is actually on average actually correct after a month, but the standard deviation is not 1 but 2 minutes. So from the quality control perspective, and in particular Taguchi quality control, which process is now the better, or which process is the best of the two? And you could say this with your own preference, but you must use the notion of expected loss to justify your choice. So you will actually not get any credit if you just guess A or B. Alright, so we worked with the quality loss function, which has three letters in it. So we have the capital X, which is a random variable modeling the production process. There is the loss coefficient K, and then there is the target value of the production. The target here is 12 o'clock noon. With this model, we have an expected loss. So in a way, in that sense, what is most on this slide is actually not part of the answer. So you don't need to write this down. What is important are the three last lines on the slide. So you can say what is theta. It is 12 noon. Then we have the mu's, the means, and the standard deviation. It's a little bit strange, but the hours and minutes. But it will work out. So you should keep in mind that what the three parameters are in the quality loss function, and then you have the production itself. The production, so the X, the capital X, has a mean mu and a standard deviation sigma. Okay, so everything is determined in this slide. So we have the X is A or B, the target is 12 o'clock, and we have all these sigmas, the standard deviations, and the mu's, the means. But what we don't have is the quality loss function. The quality loss parameter, or also called the loss coefficient. So that's that parameter K. We assume a parabola centered at 12, and the K kind of determines how wide or how narrow that parameter, that parabola is. So we have not used yet the $10 loss, so let's use that. So the loss coefficient, the units is actually a dollar. So the loss function gives a dollar amount. So if the loss is more than 3 minutes, so you can take 15 or you could take 9. At 15, then we have the loss of $10. So the loss coefficient K is 10 over 9. And then we can immediately set up the expected loss. So again, the answer is actually the bottom line, and the justification above is the interpolation. So it is an interpolation of a quadric, but there's only one coefficient. Suffices that we use only one condition. Okay, so then we apply this formula for x equals a and x equals b. And we see that the expected loss is $20 over 9 for process A, whereas for process B, where the loss of the standard deviation gives a much higher cost, even if there is no loss at missing the target. So the Taguchi quality control gives a penalty on missing the target. So the watch of type A actually misses the target by 1 minute, but it has a smaller standard deviation, and that means that compared to watches of type B, that those watches are actually better. So where the standard deviation of watches that are produced by process B, they give us a higher expected loss. So we will use process A. Okay, so another way to solve this would be via Monte Carlo simulation. So you would simply manufacture, simulate the manufacturing of 1 million watches of type A, and each time you would compute if there is a loss or not, just by looking at the each time after 1 month what would be the loss. So, but that's the question that's kind of missing from here, Monte Carlo simulation. Okay, so the second type of question involves linear programming. So linear programming has actually nothing to do with programming, but more with mathematical optimization. So here is again the modeling that is important. We have a story problem. We want to design a production plan. So a manufacturer has to produce two types of products, A and B again. The A is not so profitable as item B, so B sells for $7 per unit, whereas A only for $5 per unit. But we have constraints, so we must produce at least 20 units of A, so we cannot really focus entirely on B. And we also have the same lower bound for B. Then we are limited by our storage capacity. Also labor. B is more profitable. However, is it is takes more labor to produce. So, and we have only 600 hours of labor available. So this is the story. So what's the question now? How many units of type A and how many units of type B will you produce to maximize the profit? So that will be the primal model for this problem, for this production planning. The dual problem will look at the cost side. It will try to minimize the costs. Okay, so the first step to do is to choose the variables. So I label them as x sub A and x sub B for the number of units we produce respectively of A and B. Then we have an objective function. That's a maximization of the profit. So we will maximize the linear function 5 times x of A plus 7 times x of B. Why the 5 and the 7? Well, the profit is 5 times x of A, where x of A is everything what we produce of item A. and the term 7 times B is the contribution to the profit of the production of items of B. Okay, that's the first part. And then we look at the constraints and we translate those constraints in the inequalities. So the uh, production limits, so at least 20 and 10 of A and B, the storage capacity, and then the hours of labor. So the way you can see this here, perhaps the units are a little bit off, or they are different. So with the hours of labor, so if you would ignore the B term, so if you have only 600 hours of labor available, then you cannot make more than 300 units of item A. And you cannot make more than 200 units of item B. So as a check, so there are variations of this problem. So instead of asking you for the dual problem, I could ask you to draw the feasible region. An alternative also is to apply the solver. We have seen the Julia mathematical model optimization modeling, so the modeling, the jump modeling, so that could be an alternative question. Okay, so we go to the dual. Before you do this, you must put the maximization problem in standard form. The Julia modeling language is very flexible, but in some linear programming solvers, you really must put it into standard form. That means that a maximization problem, all the constraints are less or equal. And actually, I forgot still the constraints that the x of A and the x of B, they are both positive. So, but that was actually implicit in the x of A larger than 20, in the x of B larger than equal of 10. So, if these constraints are there, then requiring that all the variables are positive is redundant. But if that is not there, then you must actually specify those. So by default, everything is positive. You cannot produce anything negative. Okay, then once we have the standard formulation, the dual problem follows almost immediately. It's then the units here, so the constraints here. So first of all, look at the dimensions. We have 2 variables and 4 constraints. In the dual problem, we have 4 variables and 2 constraints. So the units of 5 and 7 are dollars. So we minimize costs subject to certain constraints. So that also shows that the units of y1, y3, and y1, y2, y3, y4 are actually dollar amounts. So we minimize the cost instead of maximizing the profit. So we take the transpose of the matrix. So in a way, as an intermediate step, you could write the matrix and the right-hand side vector. So this has a very shorthand notation as A less than or equal B. And then in the dual problem, you have A transpose Y larger than equal to the C transpose. So here the C is a row vector, then it becomes a column vector. Here we have a column vector that becomes then a row vector. So you can write this very compactly in the matrix vector notation. Okay, linear programming. Cost benefit analysis, where we look at an investment, the investment comes at a cost, and the cost has to be paid now. So the $3,000 is in current dollars of today. The savings or the benefits are expressed in future dollars. So we are going to have $200 every month extra. Um, what is the other data? So we have the lifespan of the equipment, 5 years, and we are using a discount rate of 3%. So the 3% is the current interest rate. So we have the alternative to put the $3,000 in a safe investment, and there is also the inflation rate. So the discount rate combines both the rate of a safe investment and the inflation. So we are interested, the bottom line is actually really what is the payback period. So after how many months do we recover our investment? So one could see here the back of the envelope would be taking 15 as 3000 divided by 200, but that doesn't take into account the discount rate. So the $200 in the future um, is has to be recalculated to the present value. And then there is the return on investment. So we expect to make that the investment will be worthwhile, but we just want to know when we get what is the payback period, and then also how sensitive would this be with the discount rate. So the payback period is also the kind of questioning a little bit the lifespan. So the lifespan is somehow expected, but what if it would break down earlier? Okay, so what is the mathematical model that we will use? We will use the we will compute the present value of the future investment. So we will do a reverse interest calculation. And now I see that I missed here, so I corrected this on the next slide, but I did not correct it here. So this formula would be a forward interest computation and should be a backward interest computation. So the I is just a counter, so we are computing the present value of the $200. Again, in the continuous compounding, we have a negative here. We are compounding monthly, so we are dividing the discount rate by 12. So again, there's a typo here. If this is positive, then this would be the future value of our $200 compounded monthly. But we will, as is clear on the next slide, in the calculations we do this right, we will use the negative exponent. So this can be done very simply in an interactive terminal session with Julia. I indicated that 15 was kind of one if there was no discount rate. So then 15 might have been, if the future dollars have the same value as the current dollars, then 15 is the answer, but that's not the case. So we define a function, so essentially translating this mathematical formula in the code. So this is where the computational side of the course comes in. 15, we are not yet there at 3000, so we need to wait 16 months after we have recovered the cost of the investment. Okay, what is now the return on investment? So the return on investment is the discount rate that yields zero savings. So we now treat the discount rate, which was 3%, as a variable. So here it's indicated in red. And we have a function that is the sum. So in a way we can do this a little bit better in the sense that there is the explicit formulation, the geometric sum, but it's okay to leave it here. So we will solve for the equation where the right hand side is 3000 and then the unknown is the discount rate. And again, the computational side of the course comes in handy. So doing this by hand is hard. You could guess again a little bit. So with an LSolve, the nonlinear solver, we define the function that defines the right hand side. So here I originally forgot the 3000, so that's why it's kind of put up here up front. So you would be, if you forget about this 3000, then you have equals 0, which is absurd. So the NL-solve is an iterative method, and we start at a discount rate of 3%. So we will compute in 10 iterations. The return on investment is 75.75% when rounded to two decimals after the dot. So this is how one should interpret this 0 here. And you can see that it gives all kinds of indications on the accuracy. So if we only needed 2 decimal places after the dot, then you see we are more than accurate enough. Okay, so we have now 3 questions solved and we are over the half of this lecture. What is still missing here is the microeconomics model. So we had questions: what if you have supply demand? What happens if there is an extra dollar of tax on the consumer or on the producer? What happens to the equilibrium? So this is a missing question. Here again, look at the midterm exam. Okay, so we considered differential equations. Imagine that you are at sea with somehow a ship that has a crack, and in the middle of the sea starts taking water in. No panic, you have a pump on board. So there's a pump on board that can pump water at 0.5 cubic meters per second. Well, the pump only activates when there was already 20 cubic meters of water inside the ship. And the rate at which the volume of water inside the ship increases is kind of 1/10 of the volume already in the ship. In a way, this is kind of a model for the crack also widening as there are more and more water coming in. Now, the question here is whether your ship will sink or not, given the story. So there are 2 parts of this question: find the correct model and then solve the ordinary differential equation. So during the course we had the failing furnace. This problem is kind of similar difficulty. In the sense that we will have a first order initial value problem. So we choose our variables, so V for the volume, T for the independent variable, time is an issue here. So I repeat the facts again. So the rate at which the volume inside the ship increases is 1/10 of the volume that is already in there. We have the pump that works at a certain rate, and then also we have the initial condition. So we have the numbers, the 1/10, the 0.5, and the 20, and you see that this bottom line here contains these three numbers. Okay, so this gives us then an ordinary differential equation, and in a Julia session, this can be very quickly solved with SymPy. So symbolic solver will actually give the solution, and the ship will sink as we have an exponential increase of water coming in. Okay, end of story, end of question. Okay, we have seen frequency domain methods where we look at a plant um, defined by a transfer function. So what is missing also here is that this transfer function can be translated into an ordinary differential equation to describe the behavior in time. So if you look at this plant, so it corresponds to a second order differential equation at the left, and at the right hand side there is some input there. So there is a right hand side function can be considered as an input. Show that this plant is unstable, and then investigate how you can stabilize the plant. So there are only two roots in the denominator by proportional feedback. So there will be one constant, one correction term that you can give to stabilize this process. Okay, why is this plant unstable? So the plant, not the plan. Well, we look at the roots. So here I did this with SymPy. There are two real roots. So that's why I say the real part of the. If you have complex conjugated roots, or yes, typically you have real coefficients, so the roots will be complex conjugated. But here in this case, both of them are real. Now you don't really see this from the left root immediately, but you see that the right root, the two terms are positive. So the plant will be unstable. So the justification for this again is that we have a second order differential equation, and where you have the s that you can interpret as an operator. In the general solution, the roots of the characteristic equation define the asymptotic long-term behavior. So if you have negative real parts, then there is decay. The solution goes to zero. But if the real parts are positive, then one has exponential growth. And the plant is unstable. Okay, how do we apply the root locus method? So in the root locus, we have a very simple proportional feedback as a controller. And then we look at the roots of the closed loop system. So we construct the transfer function. So again, you immediately, if you have to answer this question, you immediately start with this. The rest is actually explanation. So in order to make this review self-contained, I repeat the essence of what we have seen when we considered the root locus method. I will not repeat all the code, so there was a notebook posted there. Again, the notebook is probably contains way too much that you need to answer this question. In the example in class, we did this with a cubic. Here, it's actually a lot easier. We do have a quadratic. We have a quadratic polynomial parameterized in this kappa. So again, when kappa is zero, we have two real roots, and one of them is positive. At least one of them is positive. For kappa equals zero, we will not have a stable plant. But as kappa grows, the effect of this uh, compensator kicks in, and we hope that the roots actually go to the negative half plane. So this is a complex plot. So it starts from 0 to 0.1, and you can't really see this here in the picture because you only see two lines, but you have to take it from me that the blue goes to the right and the red goes to the left. So at some point these two roots will collide and transition to the complex plane. So this happens around 0.1115. I played with this a little bit. However, where these points meet, I mean, they actually do meet. So this is a problem with the resolution here. My plot was not accurate enough. But you see where they meet, actually there it is even worse. Then we have two positive real roots. So at 0.15, we are at the ends here. So at this point, the kappa is still not large enough to stabilize the plant. So when kappa equals 0.5, it is. So this is the root plot. So there are two branches. So the red one goes all the way from the right to the left. So that's the most straightforward path here. The blue starts with a negative number, then comes positive, and then the real part is still positive here, but then at this point it starts to get better. So at the kappa value 0.5, then it is stabilized. So the answer asks you to apply the root locus method. One can play a little bit with the value of kappa. The critical value, here we have a critical value, but the critical value is when the blue and the red curve actually go through zero, make these roots plots go to zero. Okay, two more questions to go, and I have less than 12 minutes left. I will make it. We have seen partial differential equations, and partial differential equations can be quite complicated, but also extremely powerful to model all kinds of processes and problems. Here is a process, or perhaps also a problem, if you like. Model the education process by a partial differential equation where we are looking at what we can quantify, and that's the distribution of the scores at time t, where t goes from the beginning of the semester to the end of the semester. So we have a cumulative probability density function where when the point range goes between 0 and 1, we can interpret this as a percentage. So we would, at the beginning of a course, we would assume that what will determine, suppose that we would be so cruel as to give, say, the final exam on the first lecture, on the first day of classes, then the scores would most likely correspond to the bell curve that mostly reflect already the individual capabilities, which say with the IQ, is normally distributed. Now, what we would like to model is that as the semester progresses, that there are two things that are happening. The profile of the bell curve will change. I say here flattens. That might not be the good thing. And also the distribution of the scores will actually also shift. So we expect that already in the middle of the semester, the scores will become better and better. So you could eventually compare the midterm scores to the final exam scores. Okay, what type of partial differential equation would you choose? So there is actually not that much choice here. We have not seen that many partial differential equations. And then how would you interpret the model? What are the critical parameters now in your model? And how would one actually idealize this? What would be those parameters that would correspond to the best education process? Okay, so here are two bell shapes. So at the left, or here at what is my left, we have what would happen at the beginning of the course. So the bell-shaped curve, this deviation would actually be quite large. So also what you will expect would be that the scores would be quite low if you would interpret space as the score, the percentage here normalized between 0 and 1. Then if somebody doesn't study, you would still get about 20% out of 100, 20%, 0.2. And you may have outliers here as well. But then as time goes on, as time equals 0, one would hope that the mean is around 80%, and that actually all the scores are very nicely distributed between 0.7 and 1. So there is the ABC distribution where half of the class would get a B, and then a quarter would get an A, and a quarter would get a C. So this would be the ideal, or close to ideal. One could say the ideal is that everybody gets an A. But here, given the circumstances that we start with this profile, we would end up with this profile here. If you want, ideally, this would be very close, the peak would be very close to, say, 0.9. So we can play with this model. Okay, what is now the partial differential equation? Well, we have the transport equation with diffusion. So we have seen the transport equation when we considered, or the advection diffusion equation, when we considered air quality modeling. So we have a transport happening. So over time, the mean in that distribution shifts to a higher value, hopefully. And also the deviation, so what I indicated earlier, that the curve flattens, is actually not a good sign. So you don't want that the change in capabilities among the students actually widens. So that's actually not such a good thing. So you would hope that the deviation actually is gradually shrinking, that everybody gets to the B level, or the average student actually gets to get a B grade. There is diffusion, and here the term diffusion is actually kind of awkward because we have the opposite process of the diffusion. So we instead of having a diffusion constant, you could speak of a concentration constant. If the K would be 0, then there wouldn't be any diffusion. Then you would actually have the same standard deviation at time equals t. Okay, so how can one interpret these parameters? So we have the uh, mean and the deviation of the distribution of the scores. They are kind of the natural solution curves that you may have. So we have the method of characteristic curves in this model, and one would have one profile that travels as we do the time simulation. What are now the parameters in this model? We have the speed and then this constant k, which would probably be called the concentration constant. So one can think of physical processes where the particles in a simulation would somehow meet each other. Instead of diffusing, they would meet each other and then they would uh, aggregate to something that is more um, dense together. All right, what is now the best education process? Well, you want a high value for speed, so you actually don't really like that you have to wait till the end of the semester for, I finally understood it. No, you hope that already by the middle of the semester there has already been significant increase. So one is quickly brought up to speed, and also you actually hope that the cohesion in the class starts to grow, that people actually uh, observe a little variation in the capabilities of what people can do. Whether that was the case in this course, I will leave up, but that's a model. All right, the last question is on machine learning. So we had 4 lectures on the introduction to machine learning. Um, Here, allow me to point at regression is actually something that is also what is missing. So Monte Carlo, no question on Monte Carlo, no question on regression or function approximation, no question on the micro and macroeconomics. So there are still gaps there, but my time is about running out. Here, assume that we are wanting to predict the geographical distribution of the outcomes of a referendum. There are 3 choices. Either people can disapprove of the question, they can approve, or they can just be not participating, which means abstaining. They are indifferent to it. Assume that from a region in a state, one had 3 different pollsters, or one collects 10 locations where everybody was against the referendum, then 10 locations where everybody was for the motion, and then 10 locations where people didn't care. So now, can you set up an electoral map? So you can't really question everybody in the state, but you have from these 30 samples, can you actually predict the outcome of the election? So you can build a model to predict this. And there are several ways to do this, but let's do this with a 2-layer neural network. And the last question is, what are the dimensions of the neural network? So this is a multi-classification problem. So we've seen 2 of them. So we had one that was a data fitting, and then we had the digits recognition. So with our first example with the data fitting, we had just two choices. Here we have 3 choices. We map the labels to 3 vectors. We have 30 data points, so we will have a 2 by 30 matrix X, and then we have the corresponding matrix Y, which for every coordinate, or where the voter was expressing the choice, we stack the corresponding vector. So that is the definition of the training data. So we have 2 inputs, the location, and then we have 3 outputs. They are the 3 coordinates of the neural network for this projection. So when we interpret the output, if you do this for a random location, we will take as outcome. So here I labeled disapprove, approve, or abstain. Whichever of these three numbers is the largest, that will be the outcome of the vote, the prediction of the vote. So it's a two-layer network. So we have always the input layer. Then we have two more layers that are coming out there. So the first layer, we have two neurons in the middle layer. And of course, we have three neurons in the output layer. So we can define the bias factors. So here I do this analytically with the dimensions of the weights, looking at the inputs and the outputs sizes. You could use flux and build the layers one after the time and chain them. Flux will tell you how many parameters there are. But here we can read off, we have the number of weights, and then we have the sizes of the bias factors. So this is a model that will use 15 parameters. Okay, and with this I have solved all the review problems. So there are 8 problems. Don't forget to at least pay attention to the oral presentations of your fellow students. So these are 8 questions. This could be a final exam, and you see that I ran through the solutions in 2 hours, in less than an hour, using extra additional explanations to make the lecture self-contained. So one could even, it's not at all, it's really possible to solve all 8 questions in the allotted time. Okay, I hope this review was helpful and does not discourage you from this final exam. Thank you for watching.